So this problem is from IMO 1972 and it's problem 1, and it basically says that if you have a set of 10 two-digit numbers, then it is always possible to select two disjoint subsets such that their members would have the same sum. So if I go ahead and randomly choose some 10 digit numbers, let's say 10, 13, 25, 27, 30, 42, 53, 69, 81, 1, 2, 3, 6, 9, one more, let's say 99. Right, so if we create a set in which we have 13 and 27, I just pick these two, and we create another set in which we have 10 and 30, right over here. We can see that both of them have the sum that is equal to 40. Right now, the surprising thing is actually that it is, no matter how you choose the 10 two-digit numbers, there will always be two subsets, disjoint subsets, such that their sum is the same. Right? And it doesn't have to be that there are two members here or two members there. It can be any number of members. The problem sort of suggests that we can somehow use the pigeonhole principle. Right, for those who do not know the pigeonhole principle, the basic pigeonhole principle basically says that if you have some n holes and you're trying to fit a pigeon into every hole, but you have n plus 1 pigeons, then there will be at least one hole which will contain two pigeons, right? And generally, if you have some n holes and a pigeons, there will be at least one hole which will have a divided by n rounded on number of pigeons, right? When I say this, it sort of looks basic, but it's actually a pretty helpful principle, right? So what we can first work towards is calculating how many distinct subsets there are, right? Once we have sort of estimated maybe that how many distinct subsets there are, and then we can check how many different sums there can be and so on. So if we have some set 10 digits, then we can have 2 to the power 10 minus 2 total number of subsets, right? 2 to the power 10 because you have 10 digits, right? And at every 10 digits you have two choices whether you include that number or not, right? So you repeat this 10 times, you have 2 to the power 10, and then I minus 2 because the subset where you exclude all of them, that is an empty set, we don't really care about that, and a subset in which you include all of them, well, then you just end up with the same set that you started with. Right, so this is the total number of subsets, and it comes down to the number 1022. So when we look at the sums, well, there can be all sorts of different sums, but if we apply the extreme principle, we can see that they will range from 10, which is the least it can be if you just chose the number 10, and it will be, okay, so let me put a dash sign. The smallest it can be is 10, and then it can go all the way to 91 plus 92 plus 93, all the way to 99, right? This number turns out to be 855, yeah. So if I'm looking at all these possible sums and they range from 10 to 855, then we can see that there are around 845 attainable sums. There can be only these many possibilities of sums, right? But then we go back to the total number of subsets. We see that clearly there are more possible subsets than there are attainable sums. And so by pigeonhole principle, we can see that there will be at least two subsets with the same sum. At least two subsets with the same sum. Right, so think of your sums as the holes, and the total number of subsets as 1022. The total number of subsets as your pigeons. So if you have 845 holes and you're assigning a pigeon to every other hole, then you will have to have at least one hole which will have at least two pigeons. In other words, there will be at least two subsets with the same sum. Right, so but we're actually not done here, because let's say A and B are the two subsets. The problem here is that A and B can have something in common. In other words, they may not be disjoint. Right, so let's say maybe A turns out, I'm just picking at random, 13, 12, 18, B turns out to be 13, 15, 38. We can see that they have 13 in common. So if I draw a proper Venn diagram, this would be A, B, then they have 13 in common, 32, 18, 15, 38. Right, I just picked numbers at random. So these two A and B's won't be the correct answer because they're not disjoint. But we can notice that since this has the sum S and this has the sum S, if we take away what's common between those two, let's say S minus 13, S minus 13, and now we end up with two different sets which are disjoint, and those that have a sum of S minus 13. So we have basically created two different subsets which have the same sum, and we are done. And so just so that I generalize this, if A and B are the two subsets, then we can create a new subset which is A minus A intersection B and B minus A intersection B, and these will be the answer to our two solutions, and we are done. QED.